Have you ever looked up in the night sky and just, I don't know if it felt that like almost a sense of vertigo, like you're staring into this massive cosmic ocean and we're just, these tiny little creatures just starting to dip our toes in.
Yeah, it's humbling, isn't it? You realize just how much is out there that we don't know, that we're just starting to grasp.
Exactly. And that's what we're diving into today, a mystery that's, well, it's kind of shaking the foundations of what we thought we knew about the universe. It's all about dark matter. Welcome to Cosmos in a Pod, the Space and Astronomy series. Please like, comment, share, and subscribe. So picture this. It's 1933, and we've got this astronomer, Fritz Zwicky. He's looking at this giant cluster of galaxies called the Coma Cluster.
Yeah, Zwicky, he was a real pioneer. I mean, this is way before we had the kind of telescopes and computing power we have today.
Right. So he's basically doing this cosmic accounting, trying to figure out, how much stuff is in this cluster and how fast everything's moving.
And that's where things get weird.
What'd he find?
Well, the galaxies, they were moving way too fast. Like,
Yeah.
based on the amount of matter he could see, the stars, the whole cluster should have just flown apart. Like, imagine a car going 200 miles per hour on a racetrack, but somehow staying perfectly on the track. It didn't make sense.
So what was holding it all together? Like some kind of cosmic speed limit?
Well, Zwicky, he proposed this radical idea. He said there must be this invisible matter out there, this stuff that we can't see but that has gravity. He called it dark matter.
Dark matter. So basically he's saying that most of the universe is made up of something we can't even see.
Yeah, and that, my friend, was the beginning of one of the biggest head scratchers in modern cosmology.
It's crazy that, I mean, this is almost a century ago, and we're still trying to figure out what this dark matter stuff actually is.
Absolutely. And it wasn't just Zwicky. Decades later, in the 1970s, we have Vera Rubin. She was studying how galaxies rotate.
Yeah, I remember reading about her work. It's like how stars orbit within a galaxy, right?
Yeah. Exactly. So think about it like a merry-go-round. You'd expect the horses on the outer edge to be moving slower than the ones near the center, right? Like, same principle with planets orbiting the sun. The farther out you go, the slower the orbital speed.
Right. Makes sense.
But what Rubin observed was that stars on the outer edges of galaxies were moving just as fast as the stars closer to the center. These flat rotation curves, they were a major puzzle.
So it's like everyone on the merry-go-round, no matter how far from the center, is somehow moving at the same speed. That doesn't sound right.
It doesn't. And that's where the dark matter idea really starts to gain momentum. It's like this invisible glue, this extra gravity that's holding those outer stars in place.
It's like the galaxy is embedded in this giant halo of dark matter.
That's it. That's the prevailing theory, known as the lambda cold dark matter model, or CDM for short. And it's not just about galaxies. It also helps explain things like gravitational lensing.
Wait, remind me about gravitational lensing. That's how light bends around massive objects, right?
Exactly. Imagine a bowling ball on a trampoline, and you roll a marble past it. The marble's path will curve slightly because the bowling ball creates a dip in the trampoline. Same thing happens in space. Massive objects like galaxies, they warp space-time, and that causes light to bend around them.
Okay, I'm starting to see how it all connects.
Yeah.
So if we observe this bending, this lensing, then that tells us there's got to be something really massive there, even if we can't see it.
Right. And the amount of lensing we observe lines up pretty well with what we'd expect if there's a lot of dark matter out there. So it seems like a pretty solid case for dark matter, right?
Yeah, it does. But you said earlier that it's still a mystery. So what's the catch?
The catch is, despite all this indirect evidence, all these signs pointing to dark matter, we've never actually directly detected it. I mean, we've built these incredibly sensitive detectors, buried deep underground, hoping to catch these dark matter particles, but so far, nothing.
So we have all these clues, but the culprit remains elusive.
Exactly. And that's what has led some scientists to wonder if maybe, just maybe, there's something else going on. Like maybe our understanding of gravity itself needs some tweaking.
Whoa. Okay, so are you saying there might be an alternative explanation for all this? Like something besides dark matter?
There might be. And that's where things get even more interesting.
All right, I'm hooked. Lay it on me.
Well, hold on tight, because next time we're diving into the realm of modified Newtonian dynamics, or MOND, a theory that dares to rewrite the rules of gravity itself. It's going to be a wild ride.
MOND. Okay, now I'm really intrigued. I can't wait to hear more about that.
Stay tuned. All right, so where were we?
we were teetering on the edge of like a cosmic cliffhanger. We've got all this evidence pointing to dark matter, but we've never actually, seen the stuff.
Right. It's like we're trying to solve a crime, but the main suspect is a ghost.
A cosmic ghost.
Yeah,
And now you're saying there might be another suspect.
there might be. And this one's a real game changer. It's called MOND, or modified Newtonian Dynamics. And it's basically saying that, well, maybe Newton got gravity slightly wrong.
Wait, Newton? Like Sir Isaac Newton? The Apple guy.
The one and only. His laws of gravity, they've worked perfectly fine here on Earth, and even for, predicting the motions of planets in our solar system. But when you get to these really, really vast distances, like the outskirts of galaxies, MOND is saying that maybe gravity doesn't behave quite the way we thought it did.
So instead of invoking this invisible dark matter, Monde is saying that gravity itself changes its tune at these massive scales.
Exactly. It's like, imagine gravity has this secret setting that kicks in when things get really, really spread out. And the crazy thing is, it actually explains those flat galaxy rotation curves we talked about. Remember, the stars on the outer edge is moving way faster than they should, and MOND can account for that.
So hold on. If MOND explains those observations, does that mean case closed, no need for dark matter?
Ugh, I wish it were that simple. MOND, while it's a very elegant theory, it has its own set of issues.
Okay, here comes the but. What kind of issues?
Well, for starters, it has trouble explaining the behavior of galaxy clusters. Those massive groups of hundreds or even thousands of galaxies all bound together by gravity.
Yeah, you mentioned those earlier. So MOND can't explain how those clusters stay together.
Not really. According to MOND, those clusters, they should be flying apart. The modified gravity it proposes just isn't strong enough at those scales to keep everything bound together.
Okay. So are you saying that even if MOND works for individual galaxies, it kind of falls apart when we look at larger structures?
That's one way to look at it. And that might be where dark matter comes back into the picture. It could be that we need both. MOND to explain the behavior of individual galaxies, and dark matter to explain those larger structures like galaxy clusters.
Are you saying a hybrid theory, MOND and dark matter working together?
It's a possibility. Some physicists are exploring those kinds of models, trying to, bridge the gap between these two seemingly contradictory ideas. It's pretty wild stuff.
Okay, my head is spinning. So we've got dark matter, MOND, and now maybe some kind of cosmic team up between the two. Is that what you're saying?
It's one of the possibilities, yeah. And that's what makes this whole debate so exciting. It's like we're constantly pushing the boundaries of what we know, trying to fit these pieces of the cosmic puzzle together.
And speaking of pushing boundaries, you mentioned some other, even more exotic ideas earlier, something about black holes and neutrinos.
Ah, yes. If we're going down the rabbit hole, we might as well explore all the tunnels, right?
Yeah.
There are some truly mind-bending ideas out there about what might be causing these cosmic discrepancies.
Okay, I'm game. Hit me with it. What other wild ideas are cosmologists exploring?
Well, one that's gained some traction is the idea of primordial black holes. These are black holes that theoretically would have formed in the very, very early universe, like fractions of a second after the Big Bang.
Primordial black holes. That sounds like something out of a sci-fi movie. How could something so old and potentially so small have such a big impact on the universe today?
That's the mind-blowing part. See, these primordial black holes, they could have a huge range of masses. Some might be tiny, but others could be, supermassive. And if they formed in those extreme conditions of the early universe, there could be tons of them out there, lurking in the shadows. And their combined gravity could be influencing the movements of galaxies and those galaxy clusters we talked about.
So it's like a cosmic treasure hunt, searching for these ancient relics that could hold the key to understanding dark matter. But wait, if they're black holes, how could we ever even find them?
It's a challenge, no doubt, but astronomers are looking for subtle clues like gravitational lensing events. Remember that bending of light we talked about?
Right, so we wouldn't actually be seeing the black holes themselves, but rather how their gravity is distorting the light from other stars.
Exactly. It's like trying to spot a tiny pebble in a pond by the ripples it makes. And these observations can give us clues about the mass and distribution of these hypothetical primordial black holes.
Wow, that is so cool. It's amazing how scientists are using these indirect methods to, piece together this puzzle. It's like they're detectives of the cosmos.
That's a great way to put it. But primordial black holes are not the only exotic candidate on the list.
Okay, lay it on me. What else is out there in this cosmic zoo of ideas?
Another candidate that has captured the imagination of physicists is the sterile neutrino.
Sterile neutrino. Okay, now that sounds even more mysterious than a primordial black hole. What even is that?
Well, you see, regular neutrinos, they're already these ghostly particles, barely interacting with matter. But sterile neutrinos, they're hypothetical particles that interact even less with regular matter. They're like the ultimate cosmic ninjas.
So they're like just slipping through the fabric of reality unnoticed.
Pretty much. And some physicists think that these stealthy particles, they could actually be a form of dark matter.
But how could something that interacts so weakly with everything else have such a big gravitational effect on the universe?
That's the million-dollar question. It all boils down to their abundance. Even though individual sterile neutrinos would rarely interact with anything, if there are enough of them out there, their combined gravity could be enough to influence the formation and evolution of galaxies and galaxy clusters.
So it's like the butterfly effect on a cosmic scale. A tiny, almost undetectable particle, multiplied by trillions upon trillions, shaping the very structure of the universe.
Exactly. And just like with primordial black holes, scientists are looking for ways to detect these sterile neutrinos, like their potential influence on the cosmic microwave background radiation.
The afterglow of the Big Bang, right? So we're talking about looking for these faint whispers from the dawn of time to solve this modern-day mystery.
Precisely. And it all highlights just how interconnected everything is, how these events from billions of years ago are still shaping the universe we see today.
So let me get this straight. We've got dark matter, MOND, primordial black holes, sterile neutrinos. It's like the cosmic buffet of possibilities.
Yeah.
But with so many options on the table, how do we even begin to narrow down the search?
Well, that's where the real fun begins, because in our next installment, we're going to dive into the cutting-edge research and the incredible new technologies that are helping us refine our theories and potentially unlock the secrets of dark matter and gravity.
All right, so we've gone deep down the rabbit hole, dark matter, MOND, primordial black holes, sterile neutrinos. It's like the universe is throwing this massive cosmic party and we're just trying to figure out the guest list.
And the guest list is pretty wild. But, the good news is we've got some pretty amazing tools to help us sort it all out.
Okay, yeah, you were about to tell us about like the cutting edge of cosmology. What kind of high-tech gadgets are we talking about?
Well, first up, we've got to talk about the James Webb Space Telescope. I mean, this thing is a game changer. It's like having a time machine, allowing us to peek back billions of years to see the very first galaxies forming.
Yeah, those images it's sending back are just mind-blowing. But how does looking that far back help us understand dark matter?
Because by studying those early galaxies, we can see how the universe evolved, how those structures, those galaxies and clusters first came together. And that gives us clues about the role dark matter might have played in all of that.
So it's like we're looking for the fingerprints of dark matter in the earliest chapters of the universe's story.
Exactly. And get this, the James Webb is already giving us some surprises. Some of those early galaxies, they seem to be a lot more massive and a lot more mature than we would have expected based on our current models.
So are those observations, are they like contradicting the dark matter idea? Or maybe we just need to tweak our understanding of how galaxies form?
That's the big question. These early galaxies, they seem to be forming stars way faster than the CDM model predicts. The one that relies heavily on dark matter.
So maybe MOND, maybe with its modified gravity, maybe can explain those early stages of galaxy formation better.
It's a possibility. The James Webb, it's really shaking things up, making us re-examine our assumptions.
Wow, it's like the universe is constantly challenging us, daring us to come up with better explanations.
Exactly. But the James Webb, it's not the only exciting new tool we have. We've also got the Vera Rubin Observatory coming online soon. This thing is going to be a dark matter hunting machine.
The Vera Rubin Observatory. Okay, tell me more about that.
Imagine a camera, right? But a camera so powerful that it can capture images of billions of galaxies in incredible detail. That's basically what the Vera Rubin Observatory is.
Billions. Wow. So it's like a cosmic census.
That's a great way to put it. It's going to scan the entire southern sky, creating this massive map of the universe, something we've never had before.
Okay, but how does mapping galaxies help us with dark matter?
Well, remember gravitational lensing, the Vera Rubin Observatory. It's going to be so sensitive that it can detect these tiny distortions in the shapes of galaxies caused by, you guessed it, the gravity of dark matter.
So it's like using the universe itself as a giant magnifying glass to see the invisible.
That's it. And by studying those distortions, those lensing effects, we can actually create a 3D map of where dark matter is concentrated in the universe.
It's like we're tracing the skeleton of the cosmos, revealing the hidden structure that's holding everything together.
And that's going to give us so much more data, so many more pieces to this cosmic puzzle.
It's amazing how scientists are finding these really clever ways to study something that we can't even see directly.
Yeah, it's a testament to human ingenuity and our endless curiosity about the universe.
So we've got all these incredible tools, all this new data pouring in. What do you think the future holds for our understanding of dark matter and the universe in general?
Well, I think we're on the verge of some truly revolutionary discoveries. I mean, think about it. Just a century ago, we didn't even know dark matter existed. And now we're building these incredible machines to map it out, to study its properties. It's an exciting time to be a cosmologist.
It really is.
Yeah.
Who knows what we'll find next? Maybe we'll finally get a definitive answer about dark matter, or maybe we'll discover something even more mind-blowing that completely changes our understanding of everything.
That's the beauty of science, isn't it? It's a never-ending journey of discovery. And who knows, maybe some of our listeners out there, maybe they'll be the ones to make those groundbreaking discoveries.
I love that. So to everyone listening, keep those minds curious, keep asking those big questions, and never stop exploring the wonders of the universe.
And if you enjoyed this deep dive into the mysteries of dark matter, make sure to follow and subscribe to Cosmos in a Pod and our YouTube channel. We've got a whole universe of incredible stories waiting to be told.
Thanks for joining us on this cosmic adventure. And as always, keep looking up.